Welcome to this walkthrough of LeetCode problem number 292, titled Nim Game. In this problem, we'll explore how to determine the winning strategy for a classic stone game, where players take turns removing 1, 2, or 3 stones from a pile. By the end of this lesson, you'll have a clear understanding of the optimal approach to solve this problem efficiently. Let's dive in. In the Nim game, you and your friend are faced with a single heap of stones on the table. The rules are simple. On each turn, a player can remove 1, 2, or 3 stones from the heap. The game continues until a player is unable to make a move, and that player loses. Now, imagine you are the one making the first move. The challenge is to determine if you can guarantee a win, assuming both you and your friend play optimally. The result should be a Boolean value: return true if you can secure a win and false if you cannot. The input is an integer, n, representing the total number of stones in the heap, where n can range from 1 to 2 billion. The output is a Boolean value indicating whether or not you can win the game under these conditions. Let's explore the first example. If the total number of stones in the heap is 4, the output is false, meaning you cannot win. Here's why: no matter how many stones you remove on your first turn, 1, 2, or 3, your friend can always remove the remaining stones, leaving none for you to take. For instance, if you remove 1 stone, 3 stones are left. Your friend can then take all 3 stones, and the game ends with you losing. Similarly, if you remove 2 stones, your friend will take the remaining 2, and if you remove 3, your friend will take the last one. In all scenarios, you are left with no winning move, and therefore, you lose the game. Now consider a second example where the total number of stones is 7. Here, the output is true, meaning you can win. To do so, you should remove 3 stones on your first turn, leaving 4 stones in the heap for your friend. This forces your friend into a losing position because, as we just saw, having 4 stones guarantees a loss if the opponent plays optimally. By carefully planning your moves to leave your friend with a heap of 4 stones, you ensure your victory. Similarly, in a third example, if there is only 1 stone in the heap, you can simply remove that stone immediately to win the game on your first turn. The key insight to solving this problem lies in understanding the importance of multiples of 4. If the total number of stones, n, is a multiple of 4, then you are forced into a losing position if your opponent plays optimally. This is because, regardless of how many stones you remove, 1, 2, or 3, you cannot prevent your opponent from returning the heap to another multiple of 4. On the other hand, if n is not a multiple of 4, you can always force a win by leaving your opponent with a heap that is a multiple of 4 after your turn. This observation provides an efficient way to determine the result. Simply check if n modulo 4 equals 0. If it does, return false; otherwise, return true. To tackle the Nim game, let's first consider a brute force approach. The intuition here is straightforward: simulate every possible move by removing 1, 2, or 3 stones and recursively evaluate the resulting game states. The goal is to determine if there exists any sequence of moves where the current player can force the opponent into a losing position. Essentially, for a given number of stones, the problem boils down to checking if there's a move that guarantees the opponent ends up in a state where they cannot win. However, while this method is conceptually simple and aligns naturally with the rules of the game, it quickly becomes computationally expensive. Exploring all potential game states results in exponential complexity, specifically O(3 to the power of n), due to the massive number of overlapping subproblems. This makes the brute force approach impractical for large values of n. Now, let's shift to a more efficient and insightful approach based on mathematical reasoning. A critical observation is that the outcome of the game depends on whether the total number of stones, n, is a multiple of 4. If n is divisible by 4, the first player is guaranteed to lose if both players play optimally. This is because, regardless of whether the first player removes 1, 2, or 3 stones, the opponent can always respond by removing stones to leave a multiple of 4 again. This pattern continues until the stones are exhausted, and the first player is forced into a losing position. On the other hand, if n is not divisible by 4, the first player can always make an initial move to leave a multiple of 4 for the opponent, effectively turning the tables and setting the second player up to lose. This insight simplifies the problem dramatically, reducing it to a single mathematical check: whether n modulo 4 equals 0. The trade-off here is that while the approach is extremely efficient, with O(1) time complexity, it relies on recognizing the underlying mathematical pattern, which may not be immediately obvious. The optimized solution leverages this mathematical insight to achieve both simplicity and efficiency. The chosen strategy involves checking whether the number of stones is a multiple of 4. If not, the first player wins, otherwise, they lose. The implementation is incredibly concise, requiring only a single line of code to perform the modulus operation. This approach runs in constant time and uses no additional space, making it optimal for all input sizes, even for values as large as 10 to the power of 9. By reducing the problem to this mathematical check, we've eliminated the need for complex simulations or recursive evaluations, making the solution highly scalable and perfect for competitive programming scenarios. To solve the Nim Game problem, the first step is to understand the game's context. This is a 2-player game where players take turns removing 1, 2, or 3 stones from a pile. The player who cannot make a move because the pile is empty loses the game. The objective is to determine if the first player can force a win, assuming both players play optimally. The next step is to define the base case. If it's a player's turn and there are no stones in the pile, that player automatically loses. This forms the fundamental base case for the recursive approach. Building on this, the recursive formulation simulates the 3 possible moves a player can make for a given number of stones, n. The player can remove 1, 2, or 3 stones, leaving n1, n2, or n3 stones, respectively. For each of these scenarios, we check if the opponent is left in a losing position. If at least one of these moves results in the opponent losing, the current player can force a win. To make this more efficient, we introduce memoization. By maintaining a table that stores results for previously computed states, we avoid recalculating outcomes for the same number of stones multiple times. In the memoization table, dp I equals true means the first player can force a win when there are I stones, while dp I equals false means they cannot. The base case is initialized with dp 0 equals false, since no stones mean the current player loses. Using an iterative dynamic programming approach, we fill the dp table for all values of n from 1 up to the given pile size n. For each I, which represents the current number of stones, we evaluate whether there is any valid move removing 1, 2, or 3 stones that leaves the opponent in a losing position. Mathematically, this is expressed as dp I equals dp I1 equals false, or dp I2 equals false, or dp I3 equals false. If any of these conditions hold true, it means the current player can force a win, so we set dp I equals true. After populating the table, the result for the given pile size n is stored in dp n. This approach ensures that the solution adheres to the principle of optimal play, where each player always aims to leave their opponent in the worst possible state. Memoization is a key insight that allows us to store intermediate results, preventing redundant calculations and reducing the overall time complexity. By using an iterative dynamic programming approach, we systematically solve all subproblems, building up to the solution for the full problem. This eliminates the overhead of recursive function calls. Additionally, the algorithm accounts for edge cases, such as when the pile size is very small, like 1, 2, or 3 stones, by explicitly handling these scenarios through the base case and transition rules. The dynamic programming array, DP, is the primary data structure used here. It stores whether the first player can force a win for each pile size from 0 to n. The size of this array is proportional to n, making its space complexity O, n. Accessing each state is constant time, O1. For time complexity, we compute each state dp I exactly once, and since there are n states, the total time complexity is O, n. However, we can further optimize space usage by recognizing that dp I depends only on the last 3 states, dp I1, dp I2, and dp I3. To optimize space, we can reduce the memory usage from O, n to O1 by storing only the last 3 values needed to calculate the current state. This eliminates the need for a full-size dp array, while still allowing us to compute the result efficiently. Another useful optimization involves pruning unnecessary checks. If all 3 previous states dp I1, dp I2, and dp I3 are true, then we know dp I will also be true, so further evaluations can be skipped. Let's summarize this with pseudocode. First, initialize the DP array. If the pile size n is 0, return false immediately because the current player loses with no stones. Otherwise, iterate through each pile size from 1 to n. For each size I, determine if any move removing 1, 2, or 3 stones leaves the opponent in a losing state. If such a move exists, mark dp I equals true. Finally, return the value of dp n, which contains the result for the given pile size. Let's walk through an example to see the algorithm in action. Consider a pile size of n equals 4. First, initialize the base case, dp 0 equals false, since no stones mean the player loses. Next, compute the results for small pile sizes. For dp 1, the player can remove 1 stone, leaving 0 for the opponent, so dp 1 equals true. For dp 2, the player can remove 2 stones, again leaving the opponent with 0, so dp 2 equals true. Similarly, for dp 3, the player can remove all 3 stones, leaving the opponent with 0, so dp 3 equals true. Now, for dp 4, all possible moves removing 1, 2, or 3 stones leave the opponent in a winning state. Therefore, dp 4 equals false. This means the first player cannot force a win when the pile size is 4. The final output is false, indicating that the first player will lose if both players play optimally. This implementation solves the LeetCode problem number 292 Nim Game in an optimal and efficient way. The function can_win_nim takes an integer n as input, representing the number of stones in the pile. The key insight to solving this problem lies in identifying the pattern of winning and losing positions based on the rules of the game. If the number of stones n is divisible by 4, the first player will always lose if the second player plays optimally. This is because no matter how many stones, 1, 2, or 3, the first player removes on their turn, the second player can always remove stones such that the total removed in each round equals 4. This eventually forces the first player into a losing position. On the other hand, if n is not divisible by 4, the first player can always win by removing a certain number of stones, 1, 2, or 3, to leave the pile in a state where n%4 equals 0 for the second player. From that point on, the first player can maintain control of the game and force the second player into a losing position. The code leverages this observation using a simple modulo operation, n%4 equals 0. If the result is true, the first player can win, otherwise, the first player will lose. This approach runs in constant time O1, as it involves only a single arithmetic operation and comparison. It is the most efficient solution possible for this problem. The function is concise and handles all edge cases, including small values of n, e.g., 1, 2, 3, and 4. For these cases, the modulo operation correctly determines the outcome based on the rules of the game. This implementation is optimal, clean, and adheres to the problem's requirements, making it well suited for competitive programming and production use. This is the Java implementation of the Nim Game problem from LeetCode. It mirrors the Python solution. With the same logic, the first player can win if the number of stones n is not divisible by 4. In this Java version, we use a method can_win_nim within a solution class, which takes an integer n as input and returns a Boolean result. The key difference compared to Python is the requirement for static typing and the explicit class structure in Java. To solve the Nim game, we need to determine if the first player can guarantee a win given a pile of n stones. Each player can remove 1, 2, or 3 stones per turn, and the player unable to make a move loses. Let's consider the example where n equals 4. Using the formula n%4 equals 0, we calculate that 4% equals 0. The result is false, meaning the first player cannot win. This happens because if there are exactly 4 stones, no matter how many the first player removes, whether 1, 2, or 3, the second player can always remove the remaining stones to leave a multiple of 4, or 0 in this case. This ensures the second player's victory, making it impossible for the first player to win. Now, let's look at the case where n equals 7. The pile starts with 7 stones, and the first player wants to leave a pile size that is not divisible by 4 for their opponent. Using the formula n%4 equals 0, the calculation 7% equals 3 gives us the result true, meaning the first player can win. Here's why: when n is not divisible by 4, the first player can always make a move to leave a multiple of 4 for the second player. For instance, the first player could remove 3 stones, leaving 4 stones in the pile. At this point, the second player is forced into a losing position because the remaining number of stones is a multiple of 4. This guarantees the first player's victory. Next, consider the example where n equals 10. Once again, the first player aims to ensure they win. Using the formula n% 4 equals 0, we calculate 10% 4 equals 2, which results in true. This means the first player can win. When n is not divisible by 4, the first player can always make a move to reduce the pile to a multiple of 4. For example, if the first player removes 2 stones, the pile is reduced to 8. Since 8 is divisible by 4, the second player is now in a losing position. The key insight here is recognizing that when n is a multiple of 4, the first player will always lose if the second player plays optimally. On the other hand, if n is not a multiple of 4, the first player can consistently force the second player into a losing situation. Finally, let's summarize the outputs for the examples we've discussed. For example 1, where n equals 4, the result is false, indicating the first player cannot win. For example 2, with n equal to 7, the result is true, meaning the first player can win. Similarly, for example 3, where n is 10, the result is also true, confirming that the first player can secure a win. These outputs align perfectly with the logic derived from the formula n% 4 equals 0 and the insights about how multiples of 4 guarantee a loss for the first player under optimal play. The time complexity of this solution is O(1), which means it operates in constant time regardless of the size of the input, n. This is because the function only performs 2 operations, a modulus operation and a comparison. First, the modulus operation n% 4 calculates the remainder when n is divided by 4, and this is a constant time operation since its execution does not depend on the value of n. Next, the result of the modulus operation is compared to 0 using a equals operator, which is also executed in constant time. Since there are no loops, recursive calls, or operations that scale with the value of n, the total time complexity remains O(1). This holds true for all cases, whether it's the best, average, or worst case, because the number of operations performed remains fixed, regardless of the input size. Now, let's consider the space complexity of the solution, which is also O(1). This means the memory usage remains constant regardless of the size of the input, n. The function does not use any additional data structures or allocate memory that grows with n. The input variable n is stored in memory, but since it is part of the input itself, it does not count as additional space. The only memory used is for the intermediate result of the modulus operation n% 4 and the result of the comparison equals 0, both of which require a fixed, constant amount of memory. Furthermore, there are no recursive calls or dynamically allocated variables that could increase the memory usage. As a result, the space complexity is O(1), ensuring that the solution is very efficient in terms of memory usage. To understand just how efficient this solution is, let's compare it to a brute force or naive approach. In a naive solution, we might simulate the game by repeatedly subtracting 1, 2, or 3 from n in all possible ways to determine if the first player can win. This would require either recursion or iteration, leading to an exponential time complexity of O(3 to the power of n, because each game state can branch into 3 possible moves. Additionally, the space complexity of such a recursive approach would be O(n) due to the recursion stack. In contrast, the optimized mathematical approach used here avoids this inefficiency entirely. By recognizing that the first player will lose if and only if n is divisible by 4, we can solve the problem in constant time. The modulus and comparison operations take constant time, and the lack of loops or recursion means the solution is exceptionally efficient with a time complexity of O(1) and a space complexity of O(1). This mathematical insight also explains why the solution works. When n% 4 equals 0, the second player can always mirror the first player's moves, ensuring that the first player loses. This makes the optimized approach both elegant and computationally superior to the brute force method. When tackling problems like the Nim Game, there are a few common mistakes to watch out for. First, developers often neglect handling edge cases, like when the input size is very small, such as n equals 1 or n equals 2, or very large, close to the upper limit of the constraints. Overlooking these scenarios can lead to runtime errors or incorrect results. The solution is to always test edge cases thoroughly, including the smallest and largest possible inputs. Another mistake is overcomplicating the solution. Beginners sometimes turn to complex data structures or dynamic programming when the problem can be solved with a simpler mathematical approach. Analyzing patterns or base cases before diving into coding can help avoid unnecessary complexity. Lastly, inefficient recursive implementations are a frequent pitfall. Without memoization, recursion can lead to exponential time complexity because of repeated calculations. To address this, use memoization or tabulation to optimize recursive solutions, reducing redundant computations and ensuring your approach is efficient. Another mistake to be wary of is misinterpreting the problem statement. It's crucial to understand whether the goal is to force a win, avoid a loss, or account for optimal play by both players. Misunderstanding this can lead to flawed logic in your solution. To prevent this, carefully read the problem constraints and verify that your solution accounts for both players playing optimally. Additionally, ignoring time and space constraints can be problematic. A solution that works well for small test cases may fail for large inputs if it has an O, n squared, or worse time complexity. Always analyze your approach and ensure it adheres to the problem's constraints. Efficient solutions are key to passing all test cases, especially when dealing with competitive programming or coding interviews. Game theory problems, like the Nim Game, often provide valuable insights for interviews. One key insight is that any problem involving turns, whether it's removing stones, choosing items, or alternating moves, typically boils down to game theory or dynamic programming. Always consider the concept of optimal play and how the opponent might try to minimize your chances of winning. Another important strategy is to identify patterns in small test cases. For example, in stone removal games, recognizing winning positions, where the current player can force a win, versus losing positions, is critical for devising a strategy. When constraints, such as n less than or equal to 10 to the power of 4, are given, focus on efficient approaches like dynamic programming with O, n, complexity or a mathematical solution. Avoid brute force unless the input size is small. Related problems include the Nim game itself, a classic example of game theory, along with the divisor game, which involves alternating moves and determining if the first player can win under similar conditions. The stone game, another variation of these problems, is more complex and often requires dynamic programming to determine if the first player can win with optimal play. Similarly, Stone Game 2 builds on this concept and demands a deeper understanding of dynamic programming to solve efficiently. Beyond these problems, alternative approaches can also be useful. For instance, mathematical pattern recognition is a powerful tool. Many turn-based problems, like the Nim game, reveal mathematical patterns such as n mod 4, which can lead to an O(1) solution that's both elegant and efficient. When mathematical patterns aren't apparent, dynamic programming can help. By breaking the problem into smaller subproblems, you can use a DP array where DP I represents whether the player whose turn it is can win with I stones remaining. This method is highly effective for constraints like n less than or equal to 10 to the power of 4, as it runs in O, n, time and space. Finally, let's consider two additional approaches. Recursive backtracking is a brute force method that simulates all possible moves. While this approach can provide correct results, it is highly inefficient for large inputs due to its exponential time complexity. It's best suited for problems with very small constraints. On the other hand, greedy approaches can sometimes offer a simpler solution. For example, choosing moves that maximize your gain or minimize the opponent's options can work well in some scenarios. However, it's important to validate greedy strategies carefully since they can break down in cases where the optimal solution requires considering future moves or patterns. Ultimately, understanding the nuances of these approaches will help you select the right strategy for each variation of turn-based games. Great job completing the walkthrough for the Nim game problem. We learned how to recognize patterns and apply mathematical reasoning to solve the problem efficiently. Remember, the optimal solution here is a constant time check, which emphasizes the power of simplifying complex scenarios. Thanks for watching, and don't forget to like, subscribe, and continue mastering your coding skills. See you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!